Hey everyone, this is a quick video going through the knock the block activity, kind of recapping and finishing it up for the clay ball so that you hopefully can do the same for the rubber ball. Now, just as a recap, we have these 10 questions it's asking us to do, and we're going through and doing each of these for both of the balls. Nicely enough, 1 and 2 are the same for both. They have the same mass. I made sure of that, and I raised them the same exact height. And so step 2 or part 2 is actually asking us to find the potential energy. So if we know the mass, we know the height, we know G, we're able to plug in for mg delta y, and we got essentially 0.12 joules. Part 3 is asking for the velocity of the ball right before it hits the block. And so we know that it's picked up in the beginning, and as each ball falls down, it loses potential energy. And where does it go? It becomes kinetic. And so right at the bottom of the arc, the instant before it hits the wooden block, it's all kinetic energy, and that must be equal to all the potential energy that there was, because we're making the assumption that there's no air resistance, right? Just kind of as a little recap here. Now, aside from that, in 4, it asked for the rebound height, which was 0 for the clay ball. It just hit and did not bounce. So if it didn't bounce, it had no velocity afterwards. 5 is asking us to find the change in momentum, which is really the impulse on the block. And there's 2 ways we can find impulse on our equation sheet. I believe it actually shows this one. Change in momentum, which is impulse, is force times the change in time. But if momentum is m times v, a change in velocity also represents a change in momentum. And so since we knew the final velocity of the ball after the collision, and we know the initial velocity of the ball just before the collision, we can do m times the change in velocity, knowing that we always have the final velocity is the first one. So this is actually like our v final, we could call it v prime, and then this is our v. And that gives us a negative change, which means that, hey, the direction flip-flopped. Now, 6 is asking us to explain why the block behaves the way it does for the ball. And so the clay ball hit, transferred all of its momentum, but it literally just was not enough for the wooden block to get knocked over. Now, 7 was asking for the free body diagram. And the short version is, hopefully you just had a ball and you had tension and gravity. Really is kind of what we're looking for. Now, to be more specific, because I know where we're headed, we need to be able to recognize that there is actually kind of this invisible little vertical here, and there's an angle between tension and that vertical. And so we can break down tension into a y and an x component that's going to help us out with our next part here. So 8 is actually asking us, and we knew that the angle was 34 degrees. I measured that. 8's asking us to find the tension in the string when the ball is just released. So that's really asking right here, just the moment of release, what's the tension in the string? And so we're going to have to look at this kind of like we would a unit 2 problem. And so in doing that, I can first off kind of just look at my pictures from above, and using sine and cosine, we can kind of make some relationships here. So I could say here that sine of my angle would be equal to force tension in the x divided by just force tension, because I'm looking at this here, or I'm looking at this one here, and I just am looking at the angle and going, well, what's the opposite? Opposite is the red, and then the hypotenuse is the blue. Similarly, we could look at cosine of our angle, and we would end up getting here that we have our force tension in the y over force tension total. That's really it. Now, with both of these, if I wanted to kind of get the tension alone, or the y and x's alone, I could just multiply both sides by ft. So I could kind of just multiply both sides by it, and there it is, force tension, the y is alone. And I could do the same likewise with the x, and then the x would be alone by just multiplying by force tension on either or both sides. And so for sake of kind of continuing this, I'm actually going to rewrite the cosine one because I know this is the one that we're going to need. Now, thinking about our forces here, if we have gravity acting on the ball down and force tension in the y acting up, those are opposing each other actually. They end up balancing each other out. They're equal but opposite. It's actually this red part, the force tension in the x direction, that keeps the ball moving along the arc. That is actually the thing that's kind of causing the motion, because the y forces or components of forces actually do cancel each other out. So if I wanted to look at the total or the net force in the y direction, here's kind of the lazy way to write it. We could say the sum of forces in the y direction. We would say that, well, we have force tension, which is going up, so we'd say that it's positive, minus the force of gravity. And if this is the net force, Newton's second law tells us that the net force is equal to m times a. But in this case, it's not accelerating up or down, so this is actually 0. In other words, force tension in the y, should have had that in green, is equal to the force of gravity. And so we can rewrite this another time. I'm going to stop color coding. We could say that force tension times cosine of my angle, this is in fact, I will color code this actually, this is the y component. I just took this and rewrote that for y, is equal to m times g. And so kind of finally here, because the goal is find the tension, finally here we end up having that the force of tension is equal to the mass times gravity divided by cosine of the angle. And lo and behold, we know all of these values. We actually know the mass, we know g, and we know the angle. So force of tension is equal to, and our mass is 0.08655 kilograms times 9.8 meters per second squared, all over cosine of 34 degrees. And I will grab my calculator. And I get a tension that is quite literally equal to 1.0 newtons. Well, a lot of work for just the number 1. So there's that. And really, this is kind of a unit 2 problem looking at part 8 here. Now, I knew that I had to look at the y components. I knew that I had to look at the y components to get tension, because that's the only one where I could set two things equal to each other. If we look at the picture here, I could have done the same thing for the x, and I would have, and please don't actually write this, but if I wanted to do the same with the x, I would have said, oh, well, the sum of forces in the x direction is equal to, and I would have just gone ahead and said force tension in the x, and that would be it. And then we'd have to say that's equal to m times a, and we don't know the acceleration, and we don't know force tension in the x, and so we have two unknowns, and so it goes nowhere. All right, so home stretch here. It's actually a lot easier now. 8 is actually the hardest part. 9. Find the centripetal acceleration of the ball at this point. Well, if we think about it and we look at our picture again, centripetal acceleration is caused by, well, a centripetal force. Centripetal force is the force point that points towards the center of the circle. And so looking here, we have this big old circle that it's like kind of like carving this arc out of. That's a terrible circle. I apologize. And so really the force that's acting towards the center along this entire path of this portion of a circle is tension along the string. We just happen to have found tension already, which is very convenient. And so we'd say that, oh, tension is the centripetal force. Ft is Fc. It is the centripetal force. So recalling that force centripetal from our previous unit is m times the centripetal acceleration. Well, solving this then, we'd say that, oh, the centripetal force over the mass gives us the acceleration. We know the force, we know the mass. We can go ahead and plug in and solve. Actually, the centripetal acceleration is equal to 1.0 newtons divided by 0.08655 kilograms. And that gives us an acceleration of 11.5 meters per second squared. But if we really are rounding for sig figs, this would be 12 meters per second squared. Now, 10, I'm actually not even going to write for mine, but I want to still answer it. Looking at the individual ball and block system, do both individual ball and block systems obey conservation of energy? I would say that the clay ball and block do not obey conservation of energy. And really, it's because that gravitational potential energy that the ball had up at the top, this energy that it has up here is dissipated. It disappears. It does not continue on to another form that we would say it could be conserved through. It ends up hitting, and then it ends up really just like smushing the darn thing, right? It ends up hitting, and it just has like a little flat spot there. So I would say no. The system of the ball and block does not obey conservation of energy, since the potential energy was dissipated into the deformation of the clay. There's also a little bit in heat. A little bit goes into, the air, but that's really kind of negligible. And a little bit goes into sound. And so I'd say no for that. Now, with this done for the clay ball, I need you to do the same exact steps for the rubber ball, knowing that the rebound height was 1 centimeter, pretty much exactly, which is pretty awesome. And I want to give a little hint for part 6 here, for why the block acts in the fashion it does. You have to keep in mind that when the rubber ball hits, it actually bounces backwards. And so if you called its original direction right before it hits positive, this rebound direction would be negative. So it'll end up having a negative momentum. So keep that in mind. And good luck with finishing this. It should not take too long. Don't overthink it. The steps are pretty much the same. Thanks.